So, good afternoon everyone. My name is Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGC Ghaziabad. So, today's topic of the today I'll discuss one of the topic of optical communication, that is a threshold condition for the laser oscillation and the laser diode rate equation. So, first of all, we'll discuss that is the threshold condition for the laser oscillation, and after that we'll discuss the laser diode rate equation of the laser. So, what is the first topic is the threshold condition for the laser oscillation. If I say condition for the laser oscillation, what is the laser oscillation? To know about the laser oscillation or threshold condition, we should first to know that what is the basic principle of laser, and that is the first basic principle of laser is the stimulated emission. Now see, if I say stimulated emission is the basic principle of the laser oscillation. For the stimulated emission, we provide a forward biasing of higher voltage, of higher energy or of higher voltage. Clear? And in the stimulated emission, two photons get released. Clear? And in the laser oscillation, there is an involvement of some spontaneous emission also, but the contribution of mainly in laser, that is the dominant is the stimulated. This is a very negligible spontaneous emission, but mainly is the stimulated emission. If I say, I can say that in laser both emissions are there, spontaneous and the stimulated, but mainly and maximum or 99% is the dominant is the stimulated emission. Clear? Means if I say what is the stimulated emission? When the electron is moved from valence band to conduction band, when electron, this is the electron, when moved from the valence band to conduction band, on getting some energy, and this energy is generally given by the forward biasing, and also from the photon also. So when this electron comes back to its initial state or in the valence band, so there is a release of photons. One photon which is exciting this one energy of one photon which excites this electron to this band, to valence band to conduction band. This photon and also another photon, when this electron moves from conduction band to valence band. So, two photons which are released are of same phase and same frequency. Clear? They both are same phase and same frequency. Clear? That's why it is known as the coherent emission. Clear? Now see, in laser oscillation, the photons will move, the photons which are released will move here, and these photons, when the energy of photon is not get enough to cross this, there is a this is a what? Mirror. and this is also one of the mirror. One mirror is partially transparent, and one mirror is fully opaque. Clear? Fully opaque means reflectivity of this mirror is 100% and reflectivity of this mirror is not 100%, it is less than the 100%. Clear? Now see, this is a cavity, and in this cavity there is a generation of photons. When the energy of photons crosses this mirror, then the photons get released from this mirror. If the energy of photon is not enough to have energy which can cross this mirror, then these photons get crossed back, and these are all more photons are generated inside the cavity, and this photon comes back. When the energy of photon gets enough or get higher, that it can cross the mirror, then it produces a laser output. Clear? Now see, so that is the threshold condition. What is the threshold condition for laser oscillation? Means threshold condition was what is the gain of this cavity, so that photon can get what is the minimum gain of the photon which can cross this mirror to get a oscillation from the laser output, and that minimum gain by the photon through which it can cross this mirror, that is known as a threshold condition. Clear? Now see, steady state conditions for a laser oscillation achieved when the gain in the amplifying medium exactly balances the total losses. Amplifying medium means this is what? This is amplifying medium. This is a mirror, and this is also one of the mirror. This is fully reflective, and this is partially reflective mirror. So in the steady state condition, when the gain in the amplifying medium, gain of the photon in the amplifying medium exactly balances the total losses, then it crosses the partial reflective mirror and produces the laser output. So a minimum threshold gain within the amplifying medium must be attained so that the laser oscillations are produced and sustained. This threshold condition or this threshold gain is determined by the change in the energy of a light beam as it passes through the amplifying medium. This threshold gain is all depend on the amplifying medium. Clear? This amplifying medium, let's say this amplifying medium is of length L. Clear? And length between the two mirrors of reflectivity R1 and R2. Let's say this has a reflectivity R1 and this is R2. This R1 is 100% and this R2 is less than 100%. Less than 100%. Okay. On each round trip, the beam passes through. On each round, 1 minute. On each round trip, the beam passes through the medium twice. Hence, the fraction loss occurred by the beam loss is, I'll tell you, is what. Now see, this is what amplifying medium. this is mirror and this is mirror having reflectivity R1 and this is having reflectivity R2. Clear? Now see, it provides a positive feedback of the photons by reflection at the mirror. At either end of the cavity there is a positive feedback from the photons, and when there is a positive feedback of the photons gain some energy. Clear? The photons which gains energy at that point when there is a same phase and the same phase shift. Clear? The optical feedback is fed back many times while receiving amplification. It passes through a medium. So in this optical photons gets amplified, energy of photon get amplifying. Clear? And this structure is known as the Fabry-Perot resonator. When the energy of photon in the amplifying medium gets enough energy so that it comes out of this mirror having reflectivity R2. So that minimum gain required, that is known as a threshold condition, and that gain which is amplifying medium should balance the losses incurred by the amplifying medium. What are the losses incurred by the amplifying medium? That is the fraction loss will be equal to R1 into R2. Fraction loss is equal to R1 into R2 e की power minus 2 into alpha into L. R1 R2 is the reflectivity of mirror, because when the photon gets hit out at this medium, at this mirror, the energy of photon loosen up due to its reflectivity and due to its reflectivity. So fraction loss, the overall loss will be equal to what? R1 into R2 e power minus 2 into alpha into L. E power minus 2 means the photons moves from here to then goes back to this one, means 2 times it crosses. Alpha is the attenuation in the amplifying medium. So fraction loss will be equal to R1 into R2 e power minus 2 into alpha into L1 L. Now what is the gain achieved by the photon in this amplifying medium? Fraction gain will be equal to e की power में 2 into G into L. So now if I say threshold, for the threshold condition, the loss should balance the gain should balance the losses. Clear? So the minimum condition for the gain should balance the losses means gain, fractional gain multiplied by fraction loss should be equal to 1. It means e की power में 2 into G into L multiply में R1 into R2 e की power minus 2 into alpha L should be equal to 1. Clear? So now see, R1 into R2 e की power में 2 into L G minus alpha is equal to 1. So I say this gain should overcome the loss, means G should overcome the attenuation. Clear? So G, the minimum gain which overcome the attenuation, means at that minimum gain, that is known as the threshold gain. So I can say that R1 into R2 e की power 2 into L into GTH minus alpha equal to 1. So on solving this equation, we'll get this threshold condition for the gain of the photon should be equal to alpha plus 1 upon twice of L natural log of 1 upon R1 into R2. On solving this, we will get this one. Clear? This R1 1 by R2 e की power comes out to be natural log of 1 upon R1 R2. Clear? Now 2L 1 by 2L plus alpha, you will get this GTH. Clear? Now next topic of the today's lecture is the laser diode rate condition. Now what is the laser diode rate conditions? As we know that in laser dominant is what? Dominant is stimulated emission. clear, but somewhat there is also spontaneous emission. Or you also can say that for the initial stage, spontaneous emission is there. When the photon gets enough energy, the energy of photon which is gained by the spontaneous emission, this energy of photon is mainly used for the stimulated emission. I can also say that like this, clear. So two-rate equation for which the electron density, rate of change of electron density in the stimulated emission in the laser is mainly due to a stimulated emission and the spontaneous emission, the rate of photon change of photon in the laser, clear. So rate of change of photon dN by dt is equal to what? Rate of change of electrons, rate of change of electrons with respect to time is equal to what? Is equal to what? Electrons injected into the laser, clear. Some electrons lose, some electrons lost due to what? These electrons lost due to what? Due to spontaneous emission. Clear? And what? And some electrons loss due to stimulated emission, and that stimulated emission is responsible for emission of photon. So I can say that dN by dt is equal to कितने इलेक्ट्रॉन्स मेरे चेंज हो रहे हैं, मैंने कितने इलेक्ट्रॉन्स दिए थे, कितने इलेक्ट्रॉन्स मेरे स्पॉन्टेनियस में यूज हो चुके, एंड कितने इलेक्ट्रॉन्स मेरे फोटोन प्रोड्यूस करने में यूज हो गए. सो मीन्स J by ED is equal to minus n by tau SP minus में C into में n into में phi. Clear? Now next rate equation is the d phi by dt is rate of change of photons with rate of change of photon with respect to time is equal to what? Is equal to the electron which are lost, the photon which is produced due to stimulated emission. These are the photons produced due to stimulated emission. Clear? And some photons are produced what? Due to what? Are produced due to spontaneous emission. Spontaneous emission. Clear? And there are losses of photons also. That photon loss is due to its photon loss due to its lifetime, because this concept you will understand when you have learned about the working principle of laser. Clear? So there are also some losses due to its lifetime. So these are the two rate diode equation, and using these two laser diode rate equation we can find out the minimum input required, minimum current density, threshold condition for the current density required to have a laser oscillation. From here we can also find out the minimum threshold condition for the current density. Clear? Now see how can we define from equation, using equation number 3. Using equation number 3 you can see that at the steady state condition, equation number 3, at the steady state condition we can say that d phi by dt comes out to be equal to what? 0 from equation number 2. This is equation number 2. Yeah. From equation number 2, we can say that d phi by dt is equal to 0 for the steady state condition. When I say d phi by dt comes out to be equal to 0, I can say Cn phi plus में Cn phi plus में delta n tau n by delta n by tau sp माइनस में phi upon में tau ph. Clear? So emission of photon due to spontaneous emission is very less, so we ignore this equation, ignore this one, and so you can say Cn phi comes out to be phi upon में tau into में ph. So you will see that the Cn comes out to be 1 upon में tau into में ph, or you can also say that n equal to 1 upon में c into में tau ph. Clear? Now see, when I say that what is the threshold condition for the electron injection, I can say this nth current density. What is the electron threshold, minimum threshold condition for the current density? When I say what is the threshold condition for the current density, I can also say this current density provides what? Electrons, related to the electrons now. So JTH is related to what? Can also be NTH. This NTH is equal to 1 upon c upon tau ph. Clear? So now this is the equation number 4. Now see, if I say apply the steady state equation to equation number 1. When I say applied the steady state equation to equation number 1, you will see that dn by dt, equation number 1, apply steady state equation and equilibrium condition, or you can say equilibrium condition. You will see that dn by dt comes out to be 0. When dn by dt comes out to be 0, then j by ed is equal to 1 minus 10 n upon me tau sp. J by ed minus me n upon me tau sp is equal to 0, and this Cn phi is equal to will also be equal to 0, because I am saying that at the threshold condition, when there is a threshold condition, it means there is no stimulated emission. When I say what is the threshold condition for the laser oscillation, it means just below threshold condition there is no stimulated emission. That's why Cn phi comes out to be equal to 0. So you will see here that at the threshold condition will be what? J by ed minus में n into में nth upon में tau sp is equal to 0. So you will see that J by ed, so as we know that nth is equal to 1 upon में c upon में tau ph. Now on putting this equation nth, you will see that you will come to know that phi s jth by ed is equal to, sorry, when I say n equal to nth, so I can also say j comes out to be jth. Clear? So jth by ed is equal to nth by tau into में sp. Now nth by tau sp, put this value in equation number 1, because if I say now I am considering what? I am considering the stimulated emission. Why I am considering the stimulated emission? Then J by equation number 1, on putting this value equation number 1, so this is equal to jth by this is equal to 0. J by ed is equal to jth by tau jth by ed minus में c into में nth into में phi. Clear? Now you will see from here, you will calculate the phi s comes out to be this one. So putting the value of C into my NTH, from here you will put the value of C into my NTH, that is equal to 1 upon my tau pH, on the putting the value of, and this comes out to be 1 upon my tau pH. And tau is what? Tau is the lifetime. So phi s comes out to be tau pH is equal to J by GD. So from this equation number 7, you will see that there is a generation of steady state photons is occurred when the current density is greater than the threshold condition for the laser oscillation. Clear? So when this current density is greater than the JTH, then only the photons will, then only that photons will produce, which is used for, which is due to stimulated emission clear. So you will see here that at this point, this is a, if I say this is a current density, if I say this is a current density, so at this point this is JTH. Before JTH there is only a spontaneous emission. After the current density, when it crosses the threshold condition for the current density, then stimulated emission will occur. Clear? So as we know that the overall threshold condition, as we know that in this equation, in this I have already told you that laser output will get what? Will be when there is a energy of photons gets balances the losses, means that there is a threshold gain which I would discuss. So this threshold gain of photon is somewhere related to what? Input threshold current density. So how it is related? So this gain, threshold gain of photon which crosses the amplifying medium, amplifying medium. Clear? Photons threshold gain, no? Threshold gain of photons which crosses the amplifying medium will be equal to what? Beta into my minimum threshold current density provided to device, yeah, LED, oh sorry, laser. Clear? So this, therefore I'll say this minimum threshold condition comes out to be, JTH comes out to be 1 upon my beta into my threshold gain. So on putting the value of GTH from this threshold condition, you will get this equation, and this graph I have already discussed. Clear? So the slides which I have prepared from is referred from this book, that is Optical Fiber Communication, Prevention Practice by John M. Senior. Thank you.